All right, so welcome to section 4.6. We're going to talk about exponential and logarithmic equations. Okay, so sort of adding to that building block of what we need to know. We know about these graphs. We know that they are they share some features, right? They're like these center points, but one of them has a horizontal asymptote and the other one has a vertical asymptote. And so what we're going to take a look at, we've actually solved some of these equations before, but like sort of a very basic level of this question. So if you want to refer back to section 4.3, we did kind of solve some exponential equations before, okay? And so what we had in those word questions or the word problems was something that was kind of like, you know, if we wanted to double our value or triple our value, right? We want to know when our money is going to get to the amount that we want it to get to. But we started with a y equals ab to the x equation. And the first thing we did to get to solve for x, we actually had to take this a and we had to move it to the other side, right? And so a is multiplied by b. So in order to move it, we would divide both sides by a. Does anyone remember how we got the x out of the exponent? Yeah, if we wanted to get this, and let me go ahead and actually highlight this. If we're solving for this x, if we want to get it out of the exponent, we're going to rewrite it in log form. And in particular, we're going to get x equals log. Does anyone remember what the base was, like what the little number is that we write here? Yeah, that's going to be a b. And then we're taking the log of whatever's on the other side, y over a. Okay. This gets our x all by itself. And this process is something we call rewrite in log form. Okay, so you'll hear me say that phrase a lot, rewrite in log form, and that's what we are meaning when we do that. Okay. The nice thing about this is we can almost go in both directions. Okay, so let's say that we had a question that looked like this. We have log little b of x equals y. And in this example, I want to get the x out of the log. If I use logs to get something out of an exponent, then I'm actually going to use exponents to get something out of the log. Okay. And so what I mean by that is if we go ahead and rewrite in exponential form, okay, what's our base going to be if we write this in exponential form? This is sort of a tricky question, right? But this base, like if we look back at the log form, where did that come from? Well, it was also the base of the exponential form. What's the power going to be here? Yeah, that power is actually going to be the thing on the other side. Okay, so b to the power of y, that, my friends, is going to equal our x value. Okay, now this is a very abstract way of looking at this because there are no numbers, right? And so we're going to go through a bunch of examples today with numbers. That's our goal. Okay. But if you want to sort of frame it for yourself in terms of like thinking about what different cases we're going to see, I made a little list over here of the different cases. Okay. So my thinking is today we're going to start with the exponential equations. And we're going to look at 3 different cases. One of the cases will have the same base. Another, we're going to use that log form. And then a third one we're going to talk about will involve factoring. Okay. So we're going to look at these 3 cases. Let's see how far we get. We may or may not get to the log equations today, and that's okay. Whatever we don't finish today, we will go ahead and finish up on Wednesday. All right. All right, so let's do some examples. All right, so solving exponential equations, we're taking a look at when the bases are equal. All right, so before I ask us to jump into an actual like exponential equation like the ones we have here, I almost want to do an example 0. Okay, let's kind of squeeze this in over here. Example 0, just to kind of think about things. If I told you that 3 to the power of x is equal to 3 to the power of 7, what would you tell me x is equal to? All right, I see one vote
7.
for 7. I hear another vote for 7. Yeah, exactly. How did you know that so quickly?
Because they have the same base.
Because they have the same base, right? And so if we look at this, we actually have 3 to some power and 3 to another power. If the bases are the same, it must be that the exponents are equal to each other, okay? And so let's go ahead and write that down. When the bases are equal, the exponents must also be equal. All right, so when the bases are equal, the exponents must also be equal. All right, so knowing that, and we take a look at example 1, I notice I have a 2 on one side, 2 on the other. What equation can I make this into? What is a simpler equation that I can turn this into? Yeah, exactly. We can take, let me get my colors correct here. X minus 1, that exponent has to be equal to the other one, 2x minus 4. And so we can write x minus 1 equals 2x minus 4. This is a nice linear equation, all right? So someone tell me how we should isolate our x here. You can either type it in the chat, you can unmute yourself, your choice. How do we find x?
You can pass over the x subtracting to the other side. So it would be 2x minus x.
Mm-hmm.
And then the negative 4 to the other side adding. So it would be negative 1 plus 4.
Good, good, good. All right, so negative 1 plus 4, that gives me 3. And then 2x minus x, that gives me 1x, right? And so we'll see that x equals 3, and we are good to go, right? All right, let's take a look at example 2. What equation could I write that would be a simpler version of example number 2? Oh, okay. So if we take a look in the chat, it looks like Dallas has said we could say 5x minus 8 equals 2 times x plus 2. Can anyone explain where this 2 is coming from? Like the 2 in front of the x plus 2? Yeah, and I think by that you mean 3 squared equals 9, yes?
Yeah.
All right, exactly. Okay, so maybe let's back up a step, right? How would we even know to do this? Can someone give me an example of an equation I should not write from here? Like what would be a wrong equation to write?
5x minus 8 is equal to x plus 2. That would be wrong.
Good. And this is incorrect for what reason?
Because they don't have the same base at that point.
Good. Incorrect because bases are not equal. Okay. So when I say like, I want us to know when to use things and why we should use things, this is a perfect example, right? So I'm sure you've heard before, oh, just set the exponents equal to each other, right? And then you kind of go along and then you get to this tricky problem and you're like, well, I just thought we had to set the exponents equal to each other. But we really need to be thoughtful about the entire phrase, right? They can only be equal when the bases are equal. And so it would be in our best interest to rewrite this almost like Jamie has, where instead of 9, we're going to write 3 squared. Okay. And so if I write this, now I have a 3 as a base on the left-hand side and on the right-hand side. Okay. This allows us to write the equation that Dallas had said a few minutes ago. 5x minus 8 equals 2 parentheses x plus 2. Okay. So sometimes it is as straightforward as example 0 or example 1, and sometimes we need to do a little bit of work. But the thing is that work might not be hard. We just have to be aware that we have to do it, right? It has to be on our radar that we can't automatically just set the exponents equal. We can only do that under certain circumstances, right? All right, so let's solve this equation here. I think it might be a good idea to, do a little distribution here. We get 5x minus 8 equals 2x plus 4, right? If we were to isolate our x, how might we go about doing that?
Subtract 2x onto both sides.
Yep, we could subtract that 2x. And then what could we do after that? Good, plus 8. Love it, love it. All right, that's going to give us 3x equals 12. And we're going to get x equals 4. Okay. So sometimes super straightforward, sometimes a little twist, but we just need to be really careful about that. All right, let's take a look at one last example here for when the bases are equal. And you might look at this and be like, that is not equal. I've seen students take a look at this question and then do something like this. Why would I write that in red?
Because of
Uh-oh.
the 1/3. Yeah, it's okay.
So that 12 I got because I did 36 minus or divided by 3. 36 divided by 3 gives me 12. However, the issue here is that this does not follow our order of operations, right? It does not follow our order of operation. That would be something that we want to be really very vigilant about, right? That we don't want to make that mistake. It happens when we're moving really quickly. But let's say for a moment that I only gave you this part, 36 times 1/3 to the x over 5. How would you know that this is an exponential function?
It follows the rule of ABX, A
Mm,
being 36, B being 1/3, and X being X over 5.
A, B, X. Good, good. I know sometimes we see the variables and then we see the numbers and we don't always make that connection real tight in our brains. But this is in fact an AB to the X power, right? And so if I wanted to start to get X by itself, in other words, I wanted to get X out of the exponent, what is one thing that we need to do in order to accomplish that? Yeah, we can divide by 36. So let's see what happens. If I divide by 36 on the left-hand side, I get 1/3 to the x over 5. Okay, that looks better. When I divide the 36 to the other side, I get 4 over 36. Okay. If we said, hey, let's simplify that right-hand side, what would we get? Yeah, we would get 1/9, right? Because 4 is smaller than 36. So 1 is smaller than 9. And it's just because I divided the top and bottom by 4, right? Okay. Now I still don't see the same base because one side has a 1/3 and the other side has a 1/9. How do I fix that?
Would you say 1/9 could also become 1/3 to the power of 2?
Ah, okay. Let's see. 1/3. If I squared that, let me just make sure I can get back to that 1/9, right? So 1 squared would give me 1. Okay, that works out. And then 3 squared would give me 9. Yeah, I agree. I think we can write it as 1/3 squared. And now we've achieved our goal. We've gotten the same base on both sides. And so we don't even need to use any logs. We can just take the left-hand exponent, set it equal to the right-hand exponent. We get x divided by 5 equals 2. All right. What is the one step we need to do in order to isolate our x? Yeah, we're going to multiply that 5 over, right? X divided by 5 means that I can multiply by 5 to get rid of it. So 2 times 5, that gives me 10. Okay. Now off to the side, I do want to show you, I know some of us really like cross multiplication, and it is a structure that can be really helpful if you know how to use it. But we only want to use cross multiplication when we have a fraction is equal to another fraction. So how would I write this right-hand side as a fraction?
Go over 1.
Yeah, I could do 2 over 1, right? And then for those of you who like the cross multiplication, you can multiply those two, you multiply these two, you know, maybe you even have your little butterfly situation, whatever makes you feel like this is going to be, you know, mathematically achievable for you. But when I multiply, I get x times 1, which is x, then 2 times 5, which gives me 10, right? So both of these structures work, but it would be important for us to just think about when do we use those and when can we not use those, all right? All right, so let's get these 3 examples on one page. We've got our example 1, 2, and 3. They work through a nice progression of pretty straightforward to we got to do a little bit of work to we got to do a little bit of that work, but also with fractions in example 3. Okay. And so when you're studying for that test next week, if all you do is look at this one and you're like, yeah, I got it, that's great, you might be doing yourself a disservice, right? We want to make sure we can go all the way through that spectrum and make those decisions. And so sometimes when I'm studying, I actually start with the harder stuff and then kind of work my way backwards. Because I know if I can do example 3, I can do example 2, and example 1 will be so easy for me, right? And that ability to say, oh, this is easy, and I can do ones that are harder, I think that helps people bring a lot of confidence, especially to like a test-taking environment, okay? All right, before we move on to the next type, let's go back up to our list for a moment. We said solving exponential equations with the same bases. And what I want to do is leave a little note here that we do not need logs. All right, that is our one case where we're not going to need to use logs, and that's okay. All right, we can do it with logs, but that will take longer than what we already did. And so much of our work is, yes, there's a lot of different ways to do something, but we want to choose the most efficient way so that we can save ourselves the most amount of time. Okay. All right, so now let's take a look at this logarithmic form. This will give us a lot more practice in what we wrote here. Okay, this will give us a lot more practice in what we wrote here. All right, so part B, when the bases are not equal, we start off with example 4 here. We have 4 to the x equals 7. What's my a value here? What's the a value here? Okay. So here's what I'm going to do. I know that we normally think about this as y equals ab to the x, right? And so I'm going to go ahead and write this as 7 equals 1 times 4 to the x. You don't have to do this part, okay? But if you're having trouble wrapping your brain around like what we're doing and the different steps, sometimes by writing in more, you can see the structure better, okay? Because now we can see like y is 7, a is 1, and b is 4, right? And so if we think back to the steps that we said at the beginning, all right, the very, very beginning, and let me just scroll up there real quick. When we have y equals ab to the x, our first step was to divide by that a. And after we divide by a, then we can rewrite it in log form. Okay, so let's remember those 2 steps and let's go back down to example number 4. All right. In this case, is it necessary to divide by A? Okay, I see one no. What are other people's thoughts? Is it necessary to divide by A? No. Okay. Can someone?
No, because it's just one.
Yeah, because it's just one. Can someone give me an example of when I would have to divide by A?
If A was any number but 1, if it was 2, or I won't say 0 because 0 is one of those confusing ones that probably should not be gotten into yet. But if it was any whole number or real number, I should say.
Yeah, any other number, right? And I do like that you made that exception for 0, because if we had a 0, then we would just have y equals 0. We wouldn't even have an exponential function. But if A is any other number other than 1, then we would have to think about dividing it, right? And so if we sort of wrote that in for ourselves, we'd have 7 over 1 equals 4 to the x, right? Which we know is the same as 7 equals 4 to the x. But how do we rewrite this in log form? We need to know what our b is, our base. And so in this case, what would we say is the base? Yeah, it's going to be a log with a base of 4. Right. The danger in my color coding is I don't always remember what colors I chose, but we're gonna call that base in purple right now. And the y value be here, and then we get our x, our variable, out of the exponent. All right. If I say, give me an exact solution, you can leave it right here. Okay. If I say, give me an exact solution, you can just say log base 4 of 7. Okay. If you want to type it into Desmos, you could get an approximate solution. You could type in log little 4 regular 7, right? We want to make sure we know how to make that 4 a little 4. But some of you might have learned some other ways to type this into a calculator, maybe like a regular calculator, where you couldn't make one number sort of smaller than the others like that. Does anyone happen to know how else you could type this into a calculator? All right. Well, let's try this, okay? Use the math button. Okay, calculators these days are definitely evolving, all right? So this next thing I'm about to show you might be completely antiquated. You might not ever have to use this, but I do want to show it to us in case we happen to get to like a really old school calculator, okay? If you have Desmos open or you have a calculator, go ahead and try typing that in and see what number you get. All right. And in particular, whatever you get here should match what you have over here. Yeah, I think it's about 1.0404, something like that. All right. And then do me another favor and try typing in this. And see what you get. And so I'm gonna stop sharing this screen. I'm gonna share my Desmo screen real quick, just so we can kind of see this. Where did it go? Great. Okay. So if you're looking in the Desmo screen right here. All right, and let's look at this left-hand side in particular. Log base set 4 of 7 gives me 1.403, blah, 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 blah. But if I type in log 7 divided by log 4, I get the same thing. But if I type in ln 7 over ln 4, I get the same thing. Okay. So just as a refresher, log gives us that common log, which means base 10. And ln gives us the natural log, and we get base, right? So the last two lines, line 2 and line 3, that might be a rule that you hear of called change of base. Okay. In particular, the second line, we're changing the base to base 10. And the third line, we're changing the base to base e. But if you find a calculator where you can't do like the subscript and make the base smaller than the other numbers, then you can use change of base to help you find those values. Okay, so we can't always control what sort of technology we have in front of us. And so it's good to know a few different ways of finding that same value. Okay. Before I exit out of the Desmo screen, are there any questions about these values? Are people getting different values or want clarification on how these work?
Can I ask you a quick question about, like, I guess the philosophy issue of things? So they're all different. I'm just struggling to understand like the basics of it here. So they're all different logarithms, and then that sort of explains how you can change from different logarithm from base to base, correct? Change of, or no?
Yeah.
I feel like I'm way off base.
Change of base just means that our calculators used to only be able to work in two bases. In fact, our calculators only used to be able to work in base 10 or base E. So this was a technology issue. So then the question is, how do you get it to do base 4? You can do a change of base so that the base is one that your calculator recognizes.
Okay. You're chipping away at it. It makes a little bit more sense.
Okay. I do want to say, for those of you who are maybe using like a TI-84, you have like a graphing calculator from your high school days, those calculators tend to open up a parentheses for you. It's one that you didn't ask it to do, but it does it automatically. If you're getting a different number and you're sitting there in the privacy of your own learning environment being like, I don't know where these numbers are coming from, it is likely because you did not close the parentheses that your calculator put there for you. So it opens it. I know you didn't open it, but you have to close it. Okay. So if you have a calculator that pops up with an, like, as soon as you type in log, it opens up a parentheses, you need to close it. Okay, and that's the same for the natural log as well. As soon as you type in natural logs, some calculators make it so that there is an automatic parentheses, and so you just have to close that. All right. But either way, any of these choices will give you about 1.404, and we would call this an approximate solution. Approximate because we rounded, there were some decimals, we did not write out every single number there. Okay. All right. Now, I prefer exact solutions, but I also understand that at some point in our lives, we may be responsible for knowing how to use the technology. That's what that other piece is. All right. This thing down here, this is all about technology and using it. But when we're thinking about solving an equation, everything we did up here is really our solution part. Okay. All right, let's take a look at a couple more examples. I think sometimes the more we do these examples, the more familiar the process gets. All right. So let's take a look at example number 5 here. Do we see clues that would lead us to believe we have an exponential function? And if we do, what are those clues?
Well, 1/3 could be b and then to the power of x.
Yeah. If we sort of zoom in on this part, we might notice that we have a b to the x. Okay. Now, I just want to be clear. Some of us are really good at identifying these things, maybe because of our previous experiences or with math or whatever it might be. Okay. And if you're sitting there being like, I don't know how people are seeing these questions are not meant to like embarrass you or put you on the spot or show you how much you don't know. Rather, the purpose of these questions is like, if we all can learn what these clues are, then we can all recognize them. Okay. And sometimes we're working with someone who's like, they just know how to do these things. They don't say it out loud exactly what they're looking for. And so I like to make sure that conversation happens so that, you know, no one is sitting here being like, I don't know how they knew that. Okay. I promise that like this identification piece, it comes with time, it comes with practice, but we have to be very intentional about it. Okay. So if we have our b to the x, is there any sort of prep work that we need to do, or can we just go ahead and rewrite it in log form right now? Minus 200. Okay, so maybe if I didn't have this 200 here, it would be easier for me to see that I have an exponential equation, right? So let's go ahead and get rid of that 200. And we get 1/3 to the power of x equals 300 minus 200 gives us 100. Okay. All right, let's compare this with what we had up here when the numbers were a little bit smaller and maybe nicer. Which number should I color in that green color for example 5? Yeah, I agree. I think this is like our y value. Which number should I color in the purple, as in which one is my base? Yeah, the 1/3 is my base. Okay. As soon as I have this in my b to the x equals a number, I can automatically rewrite in log form. Okay, rewrite in log form. So if I write it in log form, I know I'll have log. My purple number is my base. And then the green number is my regular size number. Then I think we gave our X, our variable, the yellow. And so by rewriting in log form, we got the variable out of the exponent. Okay. Now what we have right here, this, my friends, this is our exact solution. As in, if someone just asked you, hey, what number is X? You could say log base 1/3 of 100. That's your exact solution. Like you're done with the exponential log part. Okay, the rest of it is just thinking about how we use our technology to maybe get an idea of what that number actually is. Okay. And so let me shrink the screen a little bit. And I'm wondering if you could, not the decimal one, pick one of these two. Okay, pick one of these, whether you want to use the common log or the natural log, and in a direct message to me in the chat, go ahead and type in what you would type in. All right. So in other words, if you choose natural log, what would you put with the 7? What would you put in place of the 4? But if you chose common log, what would you put in place of the 7? What would you put in place of the 4? Okay. So let's do a quick technology check and see if we know what number would go where if we wanted an approximate solution. Good, I've got some answers coming in already. Remember, you can choose common log or natural log. Either one is fine. Anyone who sent me a message so far does have the correct answer. So good job. Take maybe about another 30 seconds or so to get your guess in. All right. So if we wanted to type this into the calculator, again, this is a technology issue. We could say log of the green number over log of the purple number. Right. So log of the green number divided by log of the base. And maybe that's one way you remember it, like log of the base is always on the bottom, all right? And I do want to point out one thing in particular though, and that is I can write this, or I can write this, natural log of 100 divided by natural log of 1/3. But here's what you cannot write. You cannot write log of 100 divided by natural log of 1/3. Okay. The reason why you can't do that is the whole idea behind change of base is you're changing the base of the top and the bottom to be the same. And so in the first one, you're changing them both to base 10. And in the second one, you're changing them both to base E. But in the third one, the one in the red, you changed one to base 10 and one to base E. That's why that one's in red. You can't mix and match, but you can choose one base and use that one, okay? And if you type this into the calculator, you should get about -4.192. And that would serve as your approximate solution. Okay, that would be your approximate solution. All right, so let me get example 4 and 5 on the same page for you. How we feeling with those two? Are there any questions before we move on to a new flavor of question? All right. Now, if you have questions, I know we're sort of new as a class together, right? So sometimes it's hard to be the person who asks a question. You have a few options. You can always ask me in a direct message. I will not use your name. That's okay, but it will just be a question that I'll sort of say, oh, we have a question in the chat. That's absolutely fine, right? That is one of the beauties of being in a remote learning environment, is that you can secretly whisper a question to me and nobody else has to know that you asked it, right? But sometimes we're feeling like so lost that we're like, I just don't even know what questions to ask. If you're feeling like that, a few options, office hours, okay? I know that sometimes feels weird because you're like, I'm going to go back to this person who explained things to me in a way that I didn't understand. I'm going to ask them to re-explain it to me. That can feel weird. But sometimes it's also really useful to hear it again, right? So one option is office hours. If you're feeling super overwhelmed, that is a great clue that maybe going to tutoring sessions would be helpful, right? And if you don't like those resources, we can certainly talk about other resources, but the worst sort of, the worst thing that you could do would be to sort of pretend like it's all going to be fine and just not do anything about it. Okay, so that would be the option that I hope none of us choose. I hope we choose some option that moves us forward in a constructive way. Okay. All right, so enough about that. Let's talk about example 6 here. Okay, so talk to me about example 6. What do we think? What are our ideas? Or what are some things that make this one trickier?
It reminds me of the other ones, but the bases are not the same at all.
Yeah, one base is 4, the other one's 5, right? Let's write that down. So what I hear you saying is the bases are not equal, but they're also, maybe it's not easy to make them the same. Is that accurate?
Yeah.
Okay, so bases are not equal and it's not easy to make them the same. Right? It is not easy to make them the same. Well, I think you've identified exactly the problem, right? The bases are not equal. 4 is not equal to 5, and I can't easily make them the same. And so we're going to need a different technique. Okay. And so as we listen to these different techniques, I don't want us to only listen to the technique. I want us to hear this part too. Like, how do we know that we can't just do 2x plus 3 equals x minus 2? How do we know that we can't just do some of the other tricks we've done before? Okay. So one trick that is handy in solving a lot of equations is that if we do one thing to one side, that's fine as long as we do the same thing to the other side. Okay. So our strategy here is going to be apply the same operation to both sides. Right. And so here's what I mean by that. We're going to go ahead and we're going to log both sides. All right. Now, we can use common log or natural log. It does not matter. Which one would you folks prefer that we do right now? Okay, let's do it. Right, so we'll do this one with the natural log, but we'll do the next one with the common log, just so we can see that they are going to be the same. Right, so when we say apply the same operation to both sides, we can't do like common log on one side and natural log on the other. We like literally have to do the same on both sides. So if I apply that log, I'll get natural log of 4 to the 2x plus 3 equals natural log of 5 to the x minus 2. Okay. Now, there is a very special property, I'll call it a property, of logs that you're going to learn about in the Desmos activity that's due on Wednesday. Okay. So on Wednesday, we'll sort of talk about why, but right now I'm going to pull a just believe me kind of situation. So just believe me that when we have logs and we have a power, we can take that power and we can bring it down as a coefficient. And we could do that on both sides. And so here's what that looks like. I would get 2x plus 3 times natural log of 4 equals x minus 2 times natural log of 5. I'm going to write a note for us here that this is, whoops, let's choose a color that's easier to see. This is going to be the log power property. And again, we have not learned that yet, but we will learn that on Wednesday. Okay. We want to go ahead and get x by itself. Like we're going to know we're done when we get x by itself. This next bit that we're going to do, it's going to be a very common process that we use, okay? In the sense that we are going to make things messier before we make them. Right, so we're going to make things messier before we make them better. All right, so I'm going to take this natural log of 4 and I'm going to go ahead and distribute it to the 2x and to the 3. Okay, what would be the parallel process that I could do on the right hand side? Yeah, I could do the same thing, right? But instead of natural log of 4, I would be distributing that natural log of 5. So that will go to the x and that would go to the minus 2. Okay. And we're going to take that and we're going to rewrite it. And so we'll get 2x natural log 4 plus 3 natural log 4. That's what I get on the left-hand side. What would we get on the right-hand side?
You get x times the natural log of 5 minus 2 times the natural log of 5.
Perfect. Okay. The only reason why I wanted to sort of highlight that is because normally when we distribute, we have like something in the front and then we distribute inside the parentheses. But if we have a single term at the back, we can also distribute it to the parentheses, okay? All right, now we're gonna group our like terms, okay? So in other words, can you tell me which terms have an X and which terms do not? And if we look at this, we might notice that this term has an X, but then 3 natural log 4 doesn't. But then on the other side, X natural log 5 has an X in it, and then the other one doesn't. I want us to move all the terms with an X to the same side, and I want us to move everything else to the other side. It doesn't matter which direction you move things. So let's say that we move this one, the X natural log 5, let's say we move it to the other side. How would I move this 3 natural log 4? I would subtract it, yeah. So minus 3 natural log 4, and I would do the same thing on the other side. And I would get 2x natural log 4 minus x natural log 5 equals -2 natural log 5 minus 3 natural log 4. And we'll call this step separate terms with and without x. Okay. Now, before we continue on, I'm sure there are some of you who are looking at your screen right now being like, why are there so many letters everywhere? It's so easy to get lost in this, okay? It's okay to feel uncomfortable when we use new symbols. It's okay for us to feel uncomfortable when we're like, it all just looks like a bunch of letters. Like, I promise that that's part of the learning process, okay? Embrace it. You were at a level where this is something that you were capable of, right? Because if you weren't capable of it, you wouldn't be in this class. We got to pay attention to like what our brain is telling us, not just in terms of math, but like, I can do this. I am smart enough to be able to write something like this down. I am intelligent enough to be able to write something like this down and still work with it. But it's okay if it's hard. Like that is a really important thing for us to internalize. And some of us may have spent the last many years, however many years, telling ourselves that like, I mean, I'm not good at it, so I'll just kind of like keep working. But the moment we let that like voice creep into our heads of like, I'm not good at it, man, we just shoot ourselves in the foot. Like we literally set ourselves up to not be able to do it, okay? But you're here. You took the initiative to apply for this program. You have goals, you have dreams of what you want to do, and pretty much everyone in here needs that Math 150 in the spring in order to move forward, right? If that's our goal, we have to say like, we're ready to do this, and we just kind of have to do it, okay? All right, so the beauty of clumping all these terms on the left-hand side with the X is, guess what our common factor is? I can bring an X out. And let's see what else we have left in the parentheses. I think the first term, I have 2 natural log 4. what do I have in the second term once I factor out the x?
You have -1 natural log 5.
Good, good. -1 natural log 5. Beautiful. All right, we're going to leave that grossness that is the other side. We're just going to leave it like that. Okay. Now, the catch is this. All we wanted to do was solve for x. We wanted to get x by itself. If I had this, x times 3 equals 12, what would you do to solve for x?
Divide 3 from both sides.
Yeah, you divide 3, right? And you get x equals 4. I know we all know how to do that. But look at what we have. We have, where did my colors go? We have x, right? Just like we have an x over here. In fact, we have x times 3 over here, and then x times, I don't know, some gross looking decimal over here. And what does it equal? Well, it equals a number. It equals a gross looking decimal, but it's still a number. So in other words, this is pretty much the same as this. You have to convince your brain of that. X times a number equals a number, right? X times a number equals a number. X times a number equals a number. Because we have the same setup, we can actually solve it the same way. Over here,
Yeah, that'd be great. No, I'm fully insured, so any place that takes insurance should be fine. And I also know that you can get those rapid tests at CVS for like $15, $20. I'm not sure how accurate they are, but
I think someone is unmuted. You might want to check your muted status. Cool. All right. So how do we get this x by itself down here? We do it the same way we do with that 3. We just go ahead and divide it away. All right, we just go ahead and divide it away. So we get x equals, and I know this is gross looking, but the green number divided by the gray number. And because we want an exact number, an exact solution, we just leave it like that. Okay. In fact, I think it's really good practice for us to think, okay, it's not, I don't actually know what numerical value it is. Like I didn't get to the x equals 4 stage, but I, as a mathematician, am comfortable leaving this that way. Okay. So I think what we'll do for today is we're going to go over example 17 or 7, which is very similar to example 6. And I think that's where we will finish off for today. Okay. So let me shrink this a little bit. You can see example 7 down at the bottom. And I'd like you folks in the privacy of your own learning environment to go ahead and start working through example 7. Okay, so I know I said I don't really love the monkey see, monkey do kinds of questions, but I think it's important, especially when things are sort of complicated like this, to have a little bit of that in our practice. All right, so I'll give you folks a few minutes to start working on this. And then we'll come back together and we'll start working through it together just to make sure that we're all headed in the same direction. Okay. Okay, so someone actually put a really good question in the chat. Someone asked whether they should use natural log like we did here or the common log. When I write my workout, I'm going to do it with the common log. All right. And if you want the extra practice, like to just try it with different letters, you can try it with the common log as well. Okay. All right, maybe we'll take about another 2 minutes, kind of see where we're getting. Again, I know we're all coming in with like, maybe we just took math last year, maybe it's been a really long time, right? And so being really kind and thoughtful with not just each other, but with ourselves about, it's not about being the fastest, but it is about making sure we understand each step.
Did you want us to message you the answer that we got, or
No, you
just kind of
don't.
like hold it?
We're going to go ahead and go over it right now. Okay.
Okay.
All right. So folks, I'm going to move the screen up and let's kind of take a look at what this might look like. I'm going to use common logs this time, but it is exactly the same as if you use your ln or the natural log. Okay. So I apply the same operation to both sides. And here I'm implying that I have a base 10, right? I'm implying that I don't have a base e like I had before, but that I have a base 10. I'm going to go ahead and bring that power down to the coefficient. We're going to learn about that on Wednesday. We get 2x minus 3 times log 2 equals x minus 2 times log 5. Even though the numbers are at the back, I can distribute. This is the place where I make things messier before it gets better. So we get 2x log 2 minus 3 log 2 equals x log 5 minus 2 log 5. I know that I want to clump my terms that have the x in them, because when I do that, I'm going to be able to factor out an x at the end and then divide everything else away, right? That's the whole purpose of doing that. And so I'm going to move things to the, I'm actually going to move them in a different direction than I did last time. It doesn't matter, but I just want to show us that it does not matter, okay? I'm going to go ahead and add the 2 log 5 to the left-hand side. And I'm going to subtract the 2x log 2 to the right-hand side. In doing that, I still have all my x's on one side. Okay. That means I can still factor out and x. And now everything else on this right-hand side that's what I'm going to be able to divide away. I'm going to divide it into that green term. And I'm going to end up with x equals -3 log 2 plus 2 log 5 over log 5 minus 2 log 2. Okay. Now, I wanted to do this in the opposite order for a reason. I'm betting that most of you actually have this as your answer. Is that accurate? That most people have what I just wrote down there instead of what I have in the box? Okay. So the reason why I wanted to show this, and this will be sort of our last thing for today, the reason why I wanted to show this is because both answers are correct. Okay, but sometimes when we're checking answers with other people, and let's say that one person gets this answer, but you get this other one, and then you're like, oh my gosh, I must have done it wrong. So you like erase all of your work and then you do exactly what they did, right? That can happen, especially if we feel like maybe someone else is quote unquote better at math than us, or we just feel really insecure about what we're doing. But I just want to show us that these two are actually exactly the same, okay? Here's how I know they're the same. I have all the same terms, right? I have a 3 log 2 here, and I have a 3 log 2. I have a 2 log 5, I have a 2 log 5. But the only thing that's different is the signs, right? This is a minus and then a plus. And this one is the opposite. It is plus and then minus. And if I check the denominators, same terms, but every sign is reversed, okay? If you check your answers with someone else and you have all the same terms, but every single sign is reversed, you have the same answer, okay? All that happened is that it's almost like you multiplied, whoa, let's not use x. You multiplied by -1 and you multiplied by -1. And I think we know if we take -1 and we divide it by -1, we actually get 1. So we haven't changed anything. It's just all that changes is the minus will become a plus here and the plus will become a minus here. Okay, that's the only difference between those two. So when I'm grading things, if you have like one version, but I have a different version on the answer key, but I still gave you full credit, just make sure you double check, like, is every term the same except all of the signs are different? If that is the case, then you have the same answer. Okay. All right, so I think this is a good place to stop for today. One last thing I wanted to say about, folks who are feeling maybe like class is moving really fast or you're feeling overwhelmed is I would actually go and look ahead at what we're going to be doing. Even if you're not sure what it means, sometimes looking it up or using some of those fabulous resources that you've all been finding on the interweb to kind of like hear someone else explain the problem before we do it together, sometimes that just makes it a little bit less overwhelming and a little bit easier. Okay. So take that for what it is. I'm going to go ahead and stop the recording right now.